Foundations of Mathematics for Elementary Teachers. An in-service program designed to provide background for the improvement of instruction in mathematics in the elementary schools. Prepared by E. Glenadine Gibb and Augusta Schurer, members of the Department of Mathematics, State College of Iowa in Cedar Falls. Your instructor, Glenadine Gibb.
We have studied three number systems: the whole numbers, the fractional numbers, and the integers. The whole numbers help us to answer the question of how many when we refer to sets whose members we consider to be non-divisible. If we refer to sets whose members we consider to be divisible, the fractional numbers enable us to answer the question, how many, how much? The integers describe quantities which indicate not only how much, how many, but also which of two possible choices of direction. For example, consider a line, a starting point, and a unit segment. If this is our unit segment, then we can associate with this directed segment the integer positive 1, and with this directed segment a negative 1. Let's place this directed segment on our line so that the tail coincides with our starting point. The head then coincides with a point on the line that we can label a positive 1. Using this directed segment, placing the tail at the starting point, the head corresponds to a point on the line which we can label a negative 1. If we were to use a 2-unit segment directed in this way, then the head would correspond to a point on the line which we could label a positive 2, and a segment oppositely directed would correspond to a point that we could label a negative 2. Continuing in this way, we can assign a point to every integer. Now, there's no reason that we should regard this segment that we've used here to lay off unit lengths on to the right here and to the left as being non-divisible. If we consider this to be divisible, then we can associate with this directed segment a positive 1/2, a segment such that the sum of two of these is equivalent to one with which we associated a positive 1. Placing the tail of it at our starting point, the head then corresponds to a point on the line that we can label a positive 1/2. Using an oppositely directed segment, placing it on our line in the same way, we can then label this point of our line a negative 1/2. If all the tails of our directed segments coincide with the starting point, the heads identify points which we will label with the numerals associated with the segments. Here are some of the labels. Once we've chosen a starting point and a unit of length, we can set up a correspondence between our new numbers and points on a line. We see that every point which has a label has an unlimited number of labels. For example, the point associated with the integer positive 1 has the labels of positive 1/1, positive 2/2, positive 3/3, positive 4/4, and so on. We see that there are points which can be associated with the halves, the thirds, the fourths. Every segment, no matter how long or how short, has an unlimited number of points which we can label. The new numbers named by these labels are called rational numbers. Their sums and differences can be assigned much in the same general way as sums and differences are assigned for the integers. Consider the pair positive 1/2 a negative 2/3. We could express their sum in this way. We see that they're oppositely directed and that the magnitudes or lengths are represented by fractions. Let's use other fractions so that the denominators are the same, and we can write then a positive 3/6 plus a negative 4/6. Again, oppositely directed, we find the difference of the two fractional numbers, subtracting the smaller from the greater, and using the sign associated with the greater. The sum, a negative 1/6. But let's consider the difference of this pair. We can express it in this way. As for integers, to find the difference, we add the additive inverse of the second to the first. We can write plus 1/2 then, plus a positive 2/3. Again, using other names for our fractions, we can express this as a positive 3/6 plus a positive 4/6. The same direction, we find the sum of the fractional numbers. The difference then of our pair, a positive, the common sign, a positive 7/6. But again, let's think about a line, a fixed point, a unit segment, and the idea that we can associate a point with every number. Consider this line. Let A be a starting point here. Let's mark off segments to the right and to the left. We will associate integers with these: 0, positive 1, and again to the left. If we subdivide our unit, then we can locate points which are associated with the rational numbers. The numbers which we associate with the points on the line are called coordinates of the points. For example, the coordinate of A is 0. The coordinate of B is a positive 2. The coordinate of C is a negative 3. The coordinate of D, a positive 1 3/4. The coordinate of F, a negative 1 3/4. Our coordinate system associates a point on the line with each of the rational numbers. That number serves to locate the point. Also notice the additive inverses, a positive 3, negative 3, symmetric with our starting point A, or a positive 1 3/4, a negative 1 3/4. The coordinate of this point locates a point twice as far from A as does the one whose coordinate is a negative 2 or a positive 2. But now, let's think about a plane. Can we use a coordinate system, a way of using numbers to locate points in a plane? Consider points P and Q. We see that point P is directly above a negative 2. Q is directly below a negative 2. However, Q is farther than is P. How much farther? We need to draw a second number line perpendicular to our first and through our starting point. And we can lay off segments on this line. Negative 1, negative 2, negative 3, a positive 1, positive 2, positive 3. These lines are called our axes, our vertical axis and our horizontal axis. Their point of intersection is called the origin. And now let's see if we can locate P and Q. We have here then that P is directly above a negative 2 and level with a positive 1. Its coordinate, a negative 2, 1. Q, directly below a negative 2 and level with negative 3. The coordinate, a negative 2, a negative 3. But now let's locate some other points. Say we locate a point over here we'll call R. What are the coordinates of that point? On a vertical 3, horizontal 2. The coordinate, a positive 3, a negative 2. Let's locate still another point that we'll call, say, P. 1, what's the coordinates of that point? On a vertical through 2, on a horizontal through 3. Positive 2, positive 3. Sometimes we express that just as 2, 3. The order of the coordinates makes a difference. Let's change the order. 3, 2. What point would that locate? A vertical through 3, a horizontal through 2, a point here we can call U and name the point coordinate 3, 2. What point is located by the coordinates 4, 0? A vertical through 4, a horizontal through 0, or this point here we will call S. What are the coordinates of the origin? 0, 0. Every point in the plane can be associated with an ordered pair of numbers, its coordinates. A pair of numbers can be used to locate a point in a plane. But let's consider another point. Here we have a list of points and their coordinates. Can we locate them? A negative 3, 1. Above 3, level of 1. B, a positive 2, positive 1. On a vertical through a positive 2, a horizontal through 1. C, positive 2, negative 1. A vertical through 2, a horizontal through a negative 1. And D, 3, a negative 1. A vertical through 3, a horizontal through a negative 1. We locate D. Now, we note that points on the same horizontal have the same second coordinate. Also, points on the same vertical have the same first coordinate. Let's draw line segments. AB, BC, CD. What are the measures of these line segments? For instance, the measure of line segment AB we see is 5. The measure of line segment BC, 2, and a CD, 1. But let's consider still another point. Point B. Its coordinates on a vertical through 2 and a horizontal through 1, we write 2, 1. But now let's find a point symmetric to B with respect to the vertical axis. We'll name it A. A point then whose coordinates are negative 2, 1. Let's find now a point symmetric to B with respect to the horizontal axis. We'll name it C. Its coordinates, a positive 2, a negative 1. Where is the point whose coordinates is a negative 2, negative 1? We can locate it here on a vertical through a negative 2, a horizontal through a negative 1. Let's call it D. We see here that this point is symmetric to A with respect to the horizontal axis. It's symmetric to C with respect to the vertical axis. It's symmetric to B with respect to the origin. Line segment DO, if we mark this, is congruent to line segment OB. Now, let us draw line segments AB, BC, DC, and AD. We see we have a figure here, the rectangle. The measure of this side, 2. The measure of this side, 4 of this side. The measure 2, this. The area, 4 times 2, or 8 square units. Another familiar figure is a triangle. Let's consider this. A triangle ABC, whose coordinates of A, 0, 0, of B, 5, 12, of C, 10 to 0. We can say see the measure of segment AC is 10. Suppose we draw a line from vertex B perpendicular to the opposite side. We'll mark this point of intersection D. What are the coordinates of D? It's on the same vertical as B, its first coordinate 5, and the same horizontal as A, its second 0. The measure then of this segment would be 5. What's the measure of this segment? 12. But what is the measure of segment AB? Is it the same as the measure of segment BC? We see that this measure is 5, and this is 5. If we would fold this along this line, we would see that BD would coincide with itself, and AB would coincide with BC. This is an isosceles triangle. But back to the measure. We see that this is a right angle. This would be then a right triangle. The side opposite the right angle of a right triangle is called the hypotenuse. How can we find the hypotenuse if we know the measures of the legs? Let's consider a specific right triangle, and we will start with a right angle. We'll mark along on the rays, using this as our segment, 3 units, and on this ray we'll mark off 4 units. Let's call this point X and this Y. We will draw a line segment, XY. Using our scale, we see the measure of line segment XY is 5. The measure then of this side 3, of this 4, of this 5. If we would build squares on each of these sides, this then would be 25, 16, 9. But we know that 25 is equal to 16 plus 9. Is this true for every right triangle? Let's try another. This time, let's consider this right triangle and the squares built on the sides. And then let's use these. We see that these two are congruent. Starting with this, let's place it in, and also use regions which are congruent to our given triangle. Use them in such a way we can build a square. Now let's use these two areas. Again, let's use regions which are congruent to our given triangle. Place these in this way. And we see that just as we did with this, again, we use 4 such regions. Clearly, the area of this is equal to the sum of these two. Once we have chosen a unit, the square of the measure of the hypotenuse is equal to the sum of the squares of the measures of the legs. We usually shorten this by saying that the square of the hypotenuse is equal to the sum of the squares of the legs. This useful theorem, called the Pythagorean theorem, is attributed to a Greek mathematician, Pythagoras. But now let us return to our isosceles triangle. Using this information then, 144 plus 25, which is equal to 169, must equal the measure squared of this segment. Or we would say that the measure of segment AB, also the measure of segment BC, is equal to 13. The Pythagorean theorem helps us to find measures of line segments which are neither vertical or horizontal. Let's consider this line segment. Line segment AB, whose coordinates 1, 2, and 7, 10. Let's draw a vertical through B. We'll draw a horizontal through A. Their point of intersection we will call F. What are the coordinates of that point? It's on the same vertical as B, so the first is 7. And the same horizontal as A, the second is 2. The measure then of this segment, 6. The measure of this segment, 8. What's the measure of this segment? We will call n. We know then that n squared is equal to 36, or 6 squared, plus 64, or 8 squared. Or that n is equal to 10. The measure of segment AB then is equal to 10. Using pairs of numbers to locate points gives us another way of looking at a familiar simple closed curve, the circle. Consider this circle whose center is at the origin, the radius of 10 units. We can name the coordinates of these points. First this one, which would be 10, 0. The coordinate of this point, which would be 0, 10. The coordinate of this point, which would be a negative 10, 0. and the coordinate of this point, which would be 0, a negative 10. Let's consider a point P on the circle. We see that that is on a vertical through 8, 6. Now let's draw line segment OP. We'll name this point of intersection here W. We might ask ourselves, is the point 6, 8 on the circle? We can tell then, we know that the measure squared of OP is equal to 100, since the measure of OP is 10. If it is, then 100 must equal 6 squared plus 8 squared. We see that 100 is equal to 36 plus 64, and therefore that point is on the circle. If it is on the circle, then a point symmetric to point P, we can call Q, which would have coordinates a negative 6, 8, symmetric to the vertical axis. One symmetric to the horizontal axis, let's call R, would have coordinates 6, a negative 8. And one which is symmetric with respect to the origin, we'll call S, will have coordinates a negative 6, a negative 8. We could also ask the point 9, 4, a coordinate of a point on a circle. If it is, then 81, 9 squared, plus 16, 4 squared, must equal 10 squared, or 100. We see that it is 97. 97 is less than 100. So this point does not lie on the circle, but lies inside. Again, consider another point. How about 9, 4.5? Is that a coordinate for point on the circle? Try it. Using coordinates, pairs of numbers to identify points associated with lines and plane figures helps us to describe many plane figures easily and compactly. It also enables us to use arithmetic to systematically study congruence of line segments and some of the properties of plane figures, such as parallelism, perpendicularity, and symmetry.
Foundations of Mathematics for Elementary Teachers has been presented by State College of Iowa under a grant from the National Science Foundation and prepared by E. Glenadine Gibb and Augusta Schurer, assisted by E.W. Hamilton and Diane Baum. The program was produced and directed by Robert Gabler and recorded at KDPS in Des Moines, Iowa.